Welcome. In this video, we're going to go over the 2022-2023 MAT235 practice final exam. The practice final exam that we got was curated by the instructors, and obviously I did the practice final exam as well as the actual final exam, and they happen to be quite similar, meaning a lot of the questions from the practice final exam were very representative of the questions that we saw on the actual final exam in terms of format, style, and difficulty as well, which all really just speaks towards how important it is to do the final exams. Nonetheless, let's get into it. So yeah, coverage, obviously everything. This is just from chapter 10 to chapter 16 in the Stewart textbook. Okay, first question is just multiple choice. We want to find the area of the region inside this polar curve over here to the right of the line x is equal to 0.5. So let's quickly sketch that out. Do that over here. It's not a circle. Okay, nice. Okay, and hopefully from the polar curve sketching that you've already done, you recognize that this is just a circle of radius 0.5 that's kind of slightly to the right. So this point over here is actually just 1 or 1 comma 0. Hence the line 0.5 or x is equal to 0.5 will be right over here. From there, the most direct way of doing this is to simply calculate the area of the entire circle and then dividing it by 2 to get this section right over here. So we'll do that here quickly. So we have the area, pi r squared. Radius, we can recognize that it's just 0.5, half of 1. So pi times 1/2 squared, which is just equal to pi over 4. And you'll notice that each of these options obviously will not match up with that. Hence, E is your correct answer here. Okay, next question. We want to find the sum of the absolute maximum and minimum values of this function over here on this triangular region. So our first step is to sketch the triangular region, and then next we'll try to find critical points and then classify them using the second derivative test. So that's 0, 0, 1, 0. And then 0, 1. Next, we want to label these, so L1, L2, and L3. Okay, so first we want to find where the partial derivatives, the first partials of this function with respect to x and y are equal to 0. So let's do that. So we have f sub x is equal to 0, meaning x is a variable here, meaning you see y is a constant, so we're just saying that y is equal to 0. And then similarly for f sub y is equal to 0, you just get that x is equal to 0. So what this then really tells you is that there's just a critical point at 0, 0. And yeah. With that in mind, we can check what that actually is using the second derivative test. If you were to take the second derivative of this and this, with respect to x and y, you'll get 0, and then obviously f sub xy will also be 0. So your second derivative test will effectively be, I believe, either saddle point or indeterminate. I can't quite remember which one it would be in this case, but regardless, 0, 0 is neither an absolute maximum or a minimum. Okay, let's see, what's next? Yeah, that's fine. Okay, so next we want to check the values, the maximum and minimum values along all of our lines here. So let's do that. So L1 here, we can effectively just represent as y is equal to 0 for, I guess, yeah, x is between 0 and 1. Regardless, you'll notice that it doesn't really matter what we look between. So when y is equal to 0, so we have y is equal to 0, which our function then will translate to x comma 0. So just x times 0, which is just always equal to 0. Excuse me, so we don't really have to worry about that. And just because L3 is the same, I'll do that as well. So L3, instead of y equal to 0, you have x is equal to 0, because again, it's a horizontal line. Instead, this will give you f of 0, comma y, which again is also equal to 0. So that's fine. But this basically tells us that along these two lines, our function is always basically just going to equal to 0. Okay. Next, we will look at L2, which actually has something going on. So along L2, we notice that we have a slope of -1 in this case, but we've shifted it up. So again, this point here is 1, 0. So this right here is x is equal to 1. So it's actually y is equal to -x plus 1. Meaning when we plug this in, we get f of x comma -x plus 1. And then we can actually evaluate this, right? Because this isn't just going to equal to 0. So we have x times -x plus 1, which is -x squared plus x. And notice that this is for x between 0 and 1. Next, we basically just want to find the maximum and minimum value of this new function here on this interval. One of the easiest ways of doing this, and what I've frequently actually noticed in the instructor solutions, is you simply just take the derivative and you just use the first derivative test just from Calc 1. So let's say d over dx, and then you get -2x plus 1 is equal to 0. And then when you solve for x here, you get x is equal to 0.5, or I was right, 1/2. And if we actually take a look at this, we know again that this is a parabola that opens downwards, meaning if the maximum is at 1/2, it's this is again the kind of the vertex. And because it's in the center of this interval, either 0 or 1 will produce the minimum. So this right here is the max. And then x is equal to 0 and 1. This will be the minimum. So our last step is to simply evaluate. And yeah, let me just check to make sure. Yeah, okay. So when we have this case over here, I guess I'm kind of running out of space, so I'll do it over here. So we have f of, and then when x is equal to 1/2, so notice we're evaluating this function. So when x is equal to 1/2, we have 1/2 comma -1/2 plus 1, which is 1/2. So f of 1/2 comma 1/2, which is just 1/2 times 1/2, which is equal to 1/4. The other option we have is if x is equal to 0 or 1, which you'll notice in this case it really doesn't matter which one it is. The point is one of them will be 0. So if x is equal to 0, you get 0 comma -0 plus 1, so f of 0 comma 1. If x is equal to 1, you get f of 1 comma -1 plus 1, so 1 comma 0. Regardless, you'll get either x or y equal to 0. So you get this, which is just 1 times 0, which is equal to 0. So this right here is the max, this right here is the minimum, and obviously if we add them up together, we just get 1/4, which we see is option C over here. Okay, next question. Which, if any, of the following limits is wrong? So for this one, I'll quickly tell you that immediately it is the first one, but I will go through some justification as to why the other ones are actually correct. But yeah, so quickly for A, we're just trying to show that this limit isn't actually equal to 0. So all we have to really do is just find another path in which this actually just doesn't hold. So we can see that along, let's say, y is equal to x squared. We have the following. Do I write the limit? Yeah, I guess I write the limit notation. So the limit, so instead of x comma y approaching something, it's x comma x squared. Or I guess that's the notation I think that was used. So as this approaches this point 0, 0 of our function here, so 2x squared y divided by x to the 4 plus y squared. So instead of y, we can actually just plug in x squared, which I'll do in the next step. but I'll copy this over just so it's clear. Or actually, no, it'll be quicker if I just do it this way. So this is again our initial function over here. And because we're approaching along a different path, we can replace y is equal to replace y with just x squared. So here we have x squared here. And here we have x squared squared. So simplifying this in the top, or in the numerator, we get 2x to the 4. And then in the denominator, you get x to the power 4 plus x to the power 4, which is just 2x to the 4. Notice that this simply just cancels out to 1, and obviously the limit there is then just a constant, which is 1. And the issue here is 1 obviously is not equal to 0. So in this case, that would be all the justification you need to determine that A is the correct answer. But again, because I think limits is something that you won't revisit until probably when you're studying for your final exam, it's important to actually refresh some of these things just so you don't get tripped up on the actual final exam. Okay, so that's why A is incorrect. And I'll quickly go over how to verify that B, C, and D are indeed correct. So let's go over B. So yeah, let me see. Okay, for part B, you want to make use of polar coordinates. So we actually didn't really use polar coordinates too much for solving our own limits, but just know that it is indeed there. So we'll do it quickly here. So x is r cos theta, y is r sine theta, and x squared plus y squared is r squared. So just using these three kind of equations or identities, we can effectively transform this into a slightly easier limit that we can actually work with. Apologies. Okay, so let's rewrite it. So we have 2xy over the square root of x squared plus y squared. I'll move this down a bit. Okay. Did I write equal? Yeah, we can write equals. So we have 2 times r cos theta times r sine theta. And this is all being divided by x squared plus y squared square rooted, but we know that this is effectively just r squared. So we have the square root of r squared. Simplifying this, obviously this is just r, so this will all cancel out. So all we're actually left with is just 2. Oh, sorry, no, not all of them cancel out. This right here gives you r squared, and you just have an r in the denominator, so one of them will cancel out. So you're left with 2r, I'll write them in terms of sine and cos. So sine theta, cos theta. This part I won't fully justify, but if you use squeeze theorem, again, this you can sandwich between, I believe, 0 and r, because the limit here is, so you'll notice that as x and y approach 0, r will also approach 0. You can mainly see that over here as well. And theta is kind of independent in this case. And again, it's kind of hand-wavy in this case. We didn't really prove anything, but yeah, this can again be justified using squeeze theorem. C, for this one, I'm actually not quite fully sure about this, and I most definitely have no basis for claiming this, but if you kind of recognize the similarity between this and the Calc 1 limit, limit as x approaches 0 of sine x over x, you'll notice that it's quite basically the exact same thing, but with multivariable, but with a multivariable limit. So that's honestly my only justification for this, and I'm sure there's some kind of proof that you might see in MAT237 or 257, but definitely not something you'd be concerned about in MAT235. So I'm just going to write sine x over x. Okay, and then D. Part D is just a typical squeeze theorem type of question. So I'll write the question out. So we have 2x squared y, and this is divided by x squared plus y squared. So what you want to do here is you want to start with not an identity, but an inequality that you know to be true. So in this case, x squared is most definitely less than or equal to x squared plus y squared. from here, we can manipulate. And the way you want to set this up, or how we even get this, is you notice that you have x squared plus y squared here, and you want to get an x squared in the numerator. This is kind of the way you do that. Next step, you divide both sides by this. So you get x squared divided by x squared plus y squared is less than or equal to 1. I believe. Yeah, less than or equal to 1, and then you can obviously multiply here by 2 to get that 2 in there. And then from here, we're going to, actually I'm going to move it down first so I have more space. We're going to multiply both sides by the absolute value of y, and that's kind of how we force this y to appear. So we have 2x squared. Oops, let me just make sure. So we have 2x squared, absolute value of y, x squared plus y squared, less than or equal to 2 absolute value of y. And next, we can finally expand this. This is kind of from just Calc 1, expanding the definition of a piecewise function, which in this case also is just the absolute value function. So here we have negative 2y as less than or equal to just this entire thing. So we have this equality over here. Then from here, you can use squeeze theorem yet again to conclude that this limit here is indeed equal to 0, because obviously y is going to 0. But notice that this is a composition. Simply y is being composed with the absolute value function, which is continuous. And hence that's how we can conclude that this limit here is also equal to 0, which matches up here. All right, on to the next question. Consider the graph of the given vector field f. Which of the following statements best describes the divergence of the vector field at 1, 0 and 1/2, 1/2? So first, let's obviously plot those points. So 1, 0, roughly right over here. Then 1/2, 1/2, roughly over here. So before we even look at any of the options, I'll quickly explain a relatively intuitive way to think about divergence. So your divergence is positive if when these direction vectors are going through that point, they get bigger, right? So here you see that it starts off pretty small, and then after we go through this point, it gets bigger and bigger and bigger. So that means that positive divergence. The other case is where your divergence is equal to 0. In that case, what you would see is something like this, where all of the arrows going in and out of a point are just equal, right? They're all equal, there's no change. In that case, you would have 0 divergence. You have a negative divergence when the points going into your graph are big and then they go out small. So something like this, for example. Right, so you notice that before going into that point, the vector field lines are pretty big, and as I go through that point, they get smaller and smaller. With that in mind, notice that kind of as we're tracing these through these points, they're getting bigger and bigger, right? Hopefully you do agree with that and you do see that. And looking at our options, we should then expect to see both of the divergence of f at both of these points to be positive or greater than 0. So first, we can obviously eliminate c and d just c at least. Next, we notice that, do they have 2 of the same options? Okay, well, I guess, this is either a typo or something else, but in this case, you'll notice that we have actually 2 of the same options here in A and D. I'm not sure if that was intended or not. Regardless, the point is, for the point 1/2, 1/2, the divergence of f at that point, they're all either equal to or less than 0, which obviously isn't positive. Hence, none of these options can be correct, and E is our correct final answer. So yeah, I'm not sure if the A and D being the same was intended. Regardless, E was, let me quickly check. Yeah, E was the correct answer in this case. Okay, next we want to see which of the following vector fields is not conservative. In this case, because hopefully it's almost second nature checking whether a vector field is conservative or not, I'll just quickly compute through some of these until we get to them. I think in this case it's B, but yeah, let's do this quickly. So part A, So remember, when we have a two-dimensional vector field, in this case it's pretty quick, we can just check to see if partial p or partial q partial x is equal to partial p partial y. And I think I go over the justification of why we're able to just check this in a different video, but hopefully by now you do understand that it's sufficient to check this. So partial q partial x, and here we have p and q. So partial q partial x is just 2xy, partial p partial y. In this case, here you just take the 2 down, so you also have 2xy. In this case, obviously these two are indeed equal, so this is indeed conservative. Part B, we have a three-dimensional vector field. So the quickest way, or the most, I guess, straightforward way, is to check whether the curl of this vector field is equal to 0. So really quickly, we can check the following. So yeah, so we know that the curl of f, and again, I don't remember this off the top of my head, but we'll quickly copy it down. So we have partial q partial z minus partial r partial y, and then partial r partial x minus partial p partial z, and the last part is just partial p partial y minus partial q partial x. So in this case, yeah, obviously I don't remember this off the top of my head, but if you do, again, check out one of my other videos, I go over how to quickly determine this using the cross product, which is actually how it's defined. It's defined, or a curl f is defined as the cross product between the gradient. I'm not sure if it's a gradient vector or the gradient function. Cross product with just your vector field f. So yeah, something like this. But yeah, so in this case, we can quickly compute that. So yeah, okay. So partial q partial z. Here again, we'll label all of these. So p, q, and r. So partial q partial z. So we're treating z as a variable here. So in this case, we have e to the xz times the derivative of the inside, which is just x in this case. So we have x e to the xz. And then times sine y. Make sure, yep, sine y. And then partial r partial y. So y is a variable. It doesn't even, oh no, sorry, it does appear here. So appears right over here. In this case, e to the xy times the derivative of the inside. So x e to the xy. And then cosine of z. Next, partial r partial x. So partial r partial x, same idea, except x is a variable in this case. So we have e to the xy times y. So y e to the xy. Partial r partial x. And then cos z. Minus partial p partial z. So again, e to the yz times the derivative of yz, which is just y, so y e to the yz. And then cos of y. And last we have partial p partial y. So partial p partial y. Here it gets a little annoying because they both appear, so it's a product rule in this case. Oops. So in this case we have a product rule. So we have first, so e to the yz times the derivative of the second, which is negative sine y. So I'm just going to move this over, negative sine y. First, derivative of second plus second, so cos y, times the derivative of the first, in this case, with respect to y. So we have z e to the yz. I believe z e to the yz plus y, yep, same thing. And then last portion, partial q, partial x. So here, again, take the derivative of that with respect to x. So you have e to the xz times z. So minus z e to the xz. And then sine y. And let me just quickly check. Sine y. And yeah, we're good. So here, clearly you see that this right over here, which we computed to be the curl of f, it's indeed not equal to the 0 vector, which again, as you've learned, is sufficient to conclude that f, in this case for b, is not conservative. So in this case, b is the vector field that is. Okay, question 2. The following plot shows the level sets of a function for these values of k, not too relevant. We want to sketch the gradient vector of f evaluated at these points here, a, b, c, d. So there are two main things you want to keep in mind when sketching the gradient vector. First of all, it has to be perpendicular to the point that you are drawing it at. Second of all, it has to point in the direction of increase or just maximal increase. So let's do that. For part A, we'll first of all draw a perpendicular line. So roughly over here, or it's more like a tangent line. That's what I like to think of it as. Let me check, yeah. And then in this case, to determine the direction of increase, we can simply take a look at the kind of contours or the level sets. In this case, we notice that outside is 1, 3, 5, 7. So clearly the direction of increase is kind of inwards. So from 5 to get to the kind of next level, as you might want to call it, we basically have to go straight up. And again, it has to be perpendicular. So we'll draw it in red. Actually, no, we'll just keep it in black. So it looks something like this right over here. Just like that. And then we can repeat that for B, C, and D. So here, again, roughly speaking, a perpendicular line, or sorry, kind of like a tangent line more like, sorry. And then we make sure that it's parallel. So here, notice that the kind of level set we're on right now is -1. If we were to go this way, we would actually be decreasing. So it has to be the other way. And again, it also has to be perpendicular. So roughly like that. That's another one. C, same idea. Just roughly draw something that is tangents to the point in this level curve. Notice again, if we were to go inwards here, we go from -3 to -5, meaning that's decreasing. Hence, we want to point out this way, and again, perpendicular. Just like that. And then lastly, for D, same idea. Okay, and then direction of increase, again, we're on 1 here to get the 3. We're basically going in any of these directions here. So right over there. Close enough. There we have it. So again, for these points over here, these are all, again, gradient vectors when you evaluate the gradient vector function at that point. And again, you can check based on the fact that it is A, again, perpendicular, and B, pointing in the direction of increase as well. Yes. Okay, next question for each part. Yeah, final answer, blah, blah, blah. Okay, so we want to find an equation for the tangent plane to the surface at this point. This one, quite straightforward. I'll quickly first write out the equation of the tangent plane. So let me just make sure I have it. Yeah, so we have f sub x, which is again just the derivative of our big F, which I should highlight is just this part over here. Or more like this part over here. So right in the middle. So this is basically our f. And we're not too concerned about this equal to 3 part. We're mostly concerned about the surface over here for now, I believe. Yeah. So in this case, we have f sub x evaluated at... Actually, I won't write the evaluated part, but we're basically evaluating f sub x at this point, and we're multiplying that by x minus x naught. So plus, and then f sub y, y minus y naught, and then finally f sub z, times z minus z naught, and this is equal to 0. In this case here, x, it's just x, it's a variable. X naught, y naught, z naught are just these points here. So y naught, z naught. F sub x, we can just take the partials over here. So f sub x is just equal to just x, I believe. Oops. That doesn't appear now, that's fine. Okay, so yeah, in this case, we're just taking the partial of f, which again, you'll notice is just these individual parts with respect to x. So you get 2x over x, 2x over 2, which is just x. And s sub y, same idea, it's just 2y over 4, so 1/2 y. And then f sub z, we have 2z over 3, so yeah, 2 over 3z. And then we can just plug all of this together. So actually, I'll move this down so we have enough space. Oops. Okay, so f sub x is this right over here. Evaluated at this point is just root 2. So you have root 2 times x minus x naught, which also happens to be root 2. Plus f sub y, which is 1/2 y. So 1/2 y, which is y is equal to 2, so it's just 1. So we have y minus y naught, so plus y minus 2. And then f sub z is 2 over 3 times z. I believe, yeah, 2 over 3 times z, and z here is root 3. So we have 2 root 3 over 3 times z minus z naught, which is root 3. And this right here is equal to 0. So this would be your final answer. So this one, just confirming, yeah, this one's more of a straightforward one. It's just quite literally just from the definition of the equation of a tangent plane, or just formula, I guess. But yeah. Next, we want to find f sub x of 1, 0, given this information here. So this is a multivariable chain rule question. I'll quickly sketch out, or actually, no, I think I already have it sketched out. Let me see. Oh, perfect, I already do. So we have this kind of a dependence tree, and I'll quickly fill it out. So here we have partial z, partial x. Here we have partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v, and then partial z, partial y. And because this right over here is z sub u, it's a function of u and v, we're effectively able to assume that u and v are equal to 0. Which I think this was an initial kind of point of confusion for me, but once you kind of see that, it's pretty straightforward from there. So first, I'll write a general formula for this. And again, this right here is the same thing as partial z, partial u, evaluated at the point 0, 0. And for the most part here, I'm going to just omit actually writing the evaluate part just because it gets a bit long. But yeah, so partial z, partial u. Yeah, so we can just write it out like this. And what partial z, partial u really is trying to tell you is you're trying to look for all the paths that get you from z to u effectively. So you start here, you go here and here, this is one path. You go here, and then you go here, this is another path. So we're going to multiply these two and add them with these two here multiplied together. So this is equal to, let me just check, yeah, partial z, partial x times partial x, partial u plus partial z, partial y times partial y, partial u. And in this case, if u and v are equal to 0, actually, no, we'll evaluate these first. So first of all, notice that, or I guess they used f here. Actually, let me see. Yeah, as z and u, they're pretty much synonymous in this case. You could use f here instead. That part's not as significant. Effectively, we are solving for this right over here, which is right over here. This this, and this. These are all things that we're able to solve for or that we already know. So yeah, first let's compute partial x partial u. So partial x partial u, we're simply just taking the partial derivative of this with respect to u, which is just e to the u cos v. And then you have partial z partial y, which is again just this, but with respect to y, taking the derivative. Oh, sorry, this is partial u, or sorry, partial y partial u. Apologies. So we're taking this with respect to u. So you have e to the v times cos of u. And now finally we can proceed from here. So because u and v are equal to 0, we can effectively plug these into here. If u and v are equal to 0, we have e to the 0 cos of 0. E to the 0 is 1, cos of the 0, cos of 0 is just 1. So this here is just equal to 1. So we'll keep writing that. Actually, no, let's continue the calculation over here. So first of all, we know that partial z partial u evaluated at this point is just equal to 1. So we have 1 is equal to, and again, partial z partial x is what we're solving for. Here I'll just write it as f sub x, just so we're on the same page. And then partial x partial u, we just solved here. It's here, actually I'll write it out. Yeah, but actually no, we just explained it. So yeah, this is equal to 1, so this times 1. Partial z partial y, we are given right over here, so plus 2. And then partial y partial u, same idea, we have it over here. We can just plug in 0, comma 0 again into this, so v and u are equal to 0. You'll notice we have the exact same thing. So we have e to the 0, which is 1, cos of 0, which is also just also 1. So we have 2 times 1. And just to clean things up a little bit more so it's super clear, we effectively have 1 is equal to f sub x plus 2. Meaning we can isolate for f sub x and say that f sub x is equal to negative 1. And of course this is f sub x evaluated at 1, comma 0, because if u and v are equal to 0, we can see that this is equal to 1 and this is equal to 1, meaning x comma y is equal to exactly that. So, or yeah, sorry, in this case we have 0 and 0 here. This would be 1. Here we have e to the 0 times sine of 0. Sine of 0 is obviously 0, so this entire thing here is also 0, which is again kind of where this 1, comma 0 comes from. So in this case, your answer here is just negative 1. Okay, last part here. A thin wire is bent into the shape of a semicircle. X squared plus y squared is equal to 1. X is greater than or equal to 0. The linear density is a constant k. We want to find the mass of the wire. Okay. So in this case, I'll quickly write out the formula for mass, or actually, no, we'll write out some minor things first. So first of all, our density function is rho of xy. We know it's equal to a constant k. Okay, yeah. Okay, and then here, yeah, we'll quickly write out the mass formula over here. So initially I thought you could just do a double integral here in polar coordinates, but it seemed to give me a different answer. So for now we'll just go over how you would do it using a line integral. So line integral over c of rho of xy, I believe ds, yep. So ds, this is again with respect to arc length. So our next step would be to, oh yeah, here, I'll write out the general formula here. So this, yeah. So in general, we have this right over here, f of xy ds. So it's equal to a to b, which is the limits of, or I guess the endpoints of our parameterization. And we have f of x of t, y of t. And this is multiplied by the partial, the partial, so partial x. So partial or d? Yeah, it was d. So yeah, dx dt squared plus dy dt squared. And then all square rooted. There we go, and then dt. So we're going to make use of this exact concept over here. So we clearly need to, again, find a parameterization for this curve, and then also compute these portions here. So yeah, we went with just this. So x is equal to cosine of t, y is equal to sine of t. In this case, we know that x is greater than or equal to 0. If we were to draw this circle here, we're effectively looking for this portion right over there, which can be quantified using, you can use a variety of things, but the easiest way is just to go from negative pi over 2 to positive pi over 2. Because again, remember your parameter must be increasing. So in this case, t is between negative pi over 2 and pi over 2. Okay, so next we can actually evaluate this. So we know that this is now the integral between negative pi over 2 and pi over 2 for our function, I believe just k. Yeah, k. And then now we can compute the partials really quickly. So dx dt is just negative sine t squared. And then dy dt, here it's just cosine of t. And then that's all squared, and then all under a square root here. dt, I believe that's it. Yeah. Here, notice that we get effectively sine squared t plus cos squared t, which is just equal to 1. So all we're really left with now is just the integral. Oops. From negative pi over 2 to pi over 2 of just k, and then dt. Obviously k is a constant, so we can kind of just pull it out. So we basically just have k, and then the integral inside, or the integrand inside is just 1. So we'll just put t evaluated at negative pi over 2 to pi over 2. Just k times pi over 2 minus negative pi over 2. So which, again, this is just pi over 2 plus pi over 2. So you just have k pi as your final answer. Just like that. Okay, question 4. So let f of xy be this piecewise function. We want to find the set of all points where f of xy is continuous, and of course we want to justify our answer. So with this question, we're first going to look at this portion of the piecewise first. We're going to try to justify continuity through just the continuity of rational functions first. So I'll quickly copy down the function. So we have xy plus 2x cubed plus y cubed. This is all divided by x squared plus 3y squared. Okay, so we know that this is indeed a rational function. It's a rational function, and yeah, this also does indeed imply that it is continuous on its domain. On its domain. Okay. So with this in mind, then we can first find or determine what the domain of this is. Obviously, or for any rational function, the domain is, or it's usually restricted to all real numbers except for whatever values will make the denominator 0. In this case, we have x squared plus 3y squared, both of which are all non-negative. Hence, there's no real point in trying to solve for any specific points. The only points that will give you 0 in the denominator is when both x and y are equal to 0. Right? There's no other way for that to happen, partially or mostly in part due to the fact that they're both squared. Right? So in this case, let's write that down here. So the domain of this is R2, except for the origin. So actually here, let me change the eyes here. So for now, we know that this rational function, the one we're dealing with here, is continuous on its domain, which is R2 except for the origin. We do now need to check this point right over here. We need to see if it is indeed continuous at this point, right? Because again, if it is, then it is continuous, even though it's not necessarily in the domain. because again, it's restricted to these points, right? So these points are out of the question for now, but now we have to check this point right over here, I believe. Yes. So I'll quickly write out the definition of continuity. Remember that we require that the limit as our point x comma y approaches, I do AB, yeah. So generally speaking, as we approach a point AB, function has to be equal to the function itself evaluated at that point. So the limit as x comma y approaches that point of our function has to equal to our function evaluated at that point. Okay, so next we basically just need to check the following. Limit as x comma y approaches 0, 0 of our function, which I'm just going to copy and resize. So we just need to check whether this statement right here is true. So we want to check if the limit of this function as x comma y approaches the origin, is this equal to 0? So we can quickly do this or do a quick check. Again, you could just start trying to prove it, but it's usually easier to try to find counterexamples first or paths that give you a limit otherwise. So we can try to approach, I think, yeah, approach y is equal to x. So we can approach y is equal to x. And we have the following. So because we have y approaching x, in this case, we can effectively just turn this into a single variable limit. I've seen like x comma x approaching 0, 0 being written, but you can see how this is kind of redundant, and I personally would rather just write as x approaches 0, so I'll do that for now. So as x approaches 0, and then remember here we're just replacing, wherever we see a y, we're putting an x instead. So we have x times x plus, and let's do it all at the same time. So we have x times x, which is x squared, plus 2x cubed, and then plus x cubed. In the denominator, same idea, we have x squared, and then 3y squared is just 3x squared. So now we just need to check what this limit equals to, and yeah, we can just evaluate this now. So first, we can simplify our numerator just a little bit by collecting like terms. So we have the limit as x approaches 0, and then yeah, so of 3x cubed plus x squared. And in the denominator, we just have, I believe, yeah, 4x squared, it seems. Okay. Now we can divide the numerator and the denominator by x squared. In this case, we then get the following. We have the limit as x approaches 0. So here, here, and here, this just becomes a 1 instead. So we effectively just have 3x plus 1 divided by 4. And this, we have no problems. There's no x in the denominator, so we can directly substitute this x in. So x is equal to 0. So we have 3 times 0 plus 1, or just 1 over 4. But what you'll notice is this is indeed not equal to 0. All right, so this right over here does not hold. Hence, we can then also conclude that at the point 0, 0, our function is not continuous. So this holds true so far. And then, yeah, and I believe 1, 1 is in this domain here, and we can quickly check that. So we can check. So at 1, 1. So you definitely don't need to do this because, again, 1, 1 is in all of R2 except for the origin. But if you want to just make sure, we can plug 1, 1 in. So we have 1 times 1 plus 1 cubed. So yeah, 1 times 1 plus 2 times 1 cubed, so plus 2 plus 1. All divided by 1 squared plus 3 times 1 squared. Oops. It's 1 plus 3 times 1 squared. Top obviously a 4, bottom obviously 4, so this is equal to 1. And of course, this is our function evaluated, at that point. Hence, this also does hold true. So now we can just write our concluding statement here. I guess here we can move this down and write a conclusion here first. So from this we can say, therefore, our function f cannot be continuous. It's continuous at the point 0, 0. And then obviously we have this justification over here, which again just shows that it is indeed continuous at this point. I did directly plug it in, but that's the same thing as evaluating a limit since it is continuous. Okay, and then from there we can also make our final conclusion. So therefore the set of set of all points where our function f is continuous is you could just say all of R2 except for the origin. I simply just write this in set notation. So we have x comma y in R2. R2 such that xy is not equal to 0, 0. Question 5. We want to find the surface area of the part of the paraboloid z is equal to 1 minus 2x squared minus 3y squared that lies inside this cylinder right over here. So first I'll write out the formula for surface area. So we usually write it as A of S. So A of S, where S obviously is the surface, S, and this is equal to the double integral over the region D times 1 plus, I believe we use partial z. So this is where we have our kind of function or surface as a function, as in like z or f is equal to some function of x and y. So partial z partial x squared plus partial y, partial z partial y squared. And this is all under the square root. And then dA. So seeing this, we obviously will first need to compute what partial z partial x and partial z partial y are. So we'll do that over here. Partial z partial x. In this case, this is what z is equal to, so we're just taking the partial derivative of this function with respect to x. X only appears here, so the 1 and the negative 3y effectively go away because they're constants. So we have negative 4x here. And then same idea for partial z partial y. Here, these two are effectively constants, so we just have negative 6y. Okay, now that we have this, we can plug these values into our equation here and then proceed. So we have the, again, double integral over the region D. And the region D will have, in just a second, but it does have to do with the cylinder over here. Okay, partial z partial x squared, it's just negative 4x in brackets squared. So that is 16x squared. So we have 1 plus 16x squared. And then partial z partial y in brackets squared is just, again, negative 6y in brackets squared. So we have positive 36y squared. This is all being square rooted. And then dA. Okay, so next we can take a look at our region D. In this case, we are looking at this region over here. And because it's a cylinder, it's simply just going kind of like this, up and down. And with that in mind, then we can write it out like this. So we have 16x squared plus 36y squared, it's equal to 1. Our goal here is to eventually get into polar coordinates somehow, some way, except we kind of face the issue of the fact that this isn't going to be something that's directly kind of translatable to just r and theta using x is equal to r cos theta and y is equal to r sine theta. So in this case, we actually have to do a change of variables, which is, I think, chapter 15.9, I believe, and it involves the Jacobian. So If you recall, usually actually we don't have to explain all the details, but whenever we do convert to polar coordinates, we again have to multiply by that extra r term, which is the Jacobian, and the Jacobian just change depending on the change of variables you end up doing. But yeah. So in this case, we're going to quickly rewrite this just so that it's a little more clear what the change of variables we can do is. This we can write as 4x squared. 36y squared we can write as 6y squared, and this is equal to 1. So now it's getting much closer to polar coordinates than we were before. And in this case, if we were simply just converting, let's say, to u and v, just two random variables, we could easily just set x is equal to, let's say, 1 over 4u, and y is equal to 1 over 6 v, let's say. And if we were to plug these in, we'd easily get rid of them, and we'd simply just get u squared plus v squared is equal to 1. But then we still have to take that extra step to convert that into polar coordinates. Instead, what we can do is we can just directly set these equal to r cos theta and r sin theta, and then we can solve for x and y, respectively. So let's do the change of variables here. Yeah, so we can set this equal to r cos theta. Do I need 3? No, 2 is okay. So r cos theta. And then 6y is equal to r sin theta. So again, notice that this is kind of a shortcut that leaves out a lot of work that we don't have to do instead, where if let's say we set 4x first equal to u, this equal to v, then we have to go through 2 steps of solving. Here, we can then isolate for x and y. So we know that x is equal to 1 over 4 r cos theta. Let me just check. Yeah. And then y is equal to 1 over 6 r sin theta. So the fact that we have this 1 over 4 and 1 over 6, it doesn't really change too much in terms of how we're representing this. Right? The radius here is now just a circle of radius 1, and yeah, and theta just goes between 0 and 2 pi. So we then have this over here. So r, again, just goes between 0 and 1. Theta, on the other hand, goes between 0 and pi. Or sorry, 2 pi. Yes, okay. So next we want to compute the Jacobian. So the Jacobian, and as a reminder, it looks, yes, something like this. So partial of x comma y divided by the partial of two variables, so r theta. Yes, and it looks something like, yeah, partial x, partial r, and then partial x, partial theta, partial y, partial r, and then partial y, partial theta. Right, so it's just a 2 by 2 matrix that we're taking the determinant of. Yeah, I do this all in one, I believe. Okay, so we can quickly compute each of these values. So partial x, partial r, in this case, it's simply just 1/4 cos theta. Partial x, partial theta, we're taking the derivative of theta, or sorry, not theta, of cos theta, which is negative sine theta. So we have negative 1/4 r sine theta. And then partial y, partial r, same idea, except in this case it's 1/6 sine theta. And then for partial y, partial theta, it's simply 1/6 r cos theta. Okay, and now we can quickly compute this over here. Yeah, so we end up getting 1/24r. So we just multiply these two here together, so you get 1/24 r cos squared theta. And then we're going to subtract, and then this times this, but because there's a negative over here, it just becomes plus. So plus, and then 1/24 r sine squared theta. And hopefully you don't need to see this written out directly, and in fact I won't write it out directly, but hopefully you can see that this is equal to 1 over 24 r, and you get this by factoring out the 1 over 24 r, and then you get sine squared theta plus cos squared theta, which obviously is 1. So this right here is our Jacobian, and that'll help us do our change of variables. Okay, so now we can actually finish computing this right over here. Yeah, so we just directly go into, let's do it. So we have our region over here, and we have our change of variable right over here. So we can proceed. So again, in this case, it's not r, but 1 over 24 r, and then dr d theta. So theta is on the outside. Theta goes between 0 and 2 pi. And then r goes between 0 and 1. And then we have our function right over here. But remember, we do have our change of variables that we are doing. So wherever we see x or y, we're replacing with 1 over 4 r cos theta and 1 over 4 r sine theta. Sorry, 1 over 6, excuse me, r sine theta, respectively. So in this case, we have, yeah, let's write it out the full way. So we have 1 plus, and then here we just have 16 times this quantity, this quantity here, squared. So 16 times, and then this squared here, it's just each of the components squared. So we have 1 over 16 r squared cos squared theta. And then we have 36y squared. So pretty similar idea here. So we have 32, where's the 36? Yeah, sorry, 36. So 36y squared, y is 1 over 6. R sine theta, so squaring each of those, we have 1 over 36. R squared sine squared theta. Yep, and that's it. Let me move this up a bit. It's better. And then don't forget to multiply by the Jacobian, which we solved for right over here. So times 1 over 24 r. And then here comes the dr d theta. So from this step, we have a lot of simplifications we can make. 16 and 16 will cancel. 36, 36 cancel. And then exactly as before, we can factor out an r squared, and then what we're left with is r squared times sine squared theta plus cos squared theta, which obviously is just 1. So our next step then simplifies to the following. And yeah, we can also factor out, or just move this 1 over 24 out to the front. So we have 1 over 24, or this bit over here, times the integral 0 to 2 pi, and then 0 to 1, and then we just have 1 plus r squared, all under the square roots, times r, and then dr d theta. Hopefully from here you notice that we can pretty easily integrate this because we have r and r squared. We can do a quick u substitution, which is again another benefit of just directly going to r and theta. You reserve, or sorry, you don't reserve, but you leave u open to use for your typical u substitution. So you can set u is equal to 1 plus r squared, and then du here then obviously would be 2r, and then dr, 2r dr. So yeah, we're not actually making the substitution, but, or actually we are, but this is just for evaluating this part of the integral right over here. So to make that happen, we would need a 2 multiplied here, which means we can multiply the outside by 1/2 to effectively multiply by 1. So here we now have 1 over 48 times the integral, I can do better, good enough, 0 to 2 pi. This on the inside over here, if you imagine we did multiply by this 2, we would effectively have the square root of u and then du. So we can integrate that to get 2 over 3. Here, yeah, we'll write it all out, I think. Yeah, so 2 over 3. And then it would be u, but I'm just going to put 1 plus r squared. Same thing. The 3 over 2, I believe 3 over 2. Yep. And then this is being evaluated at r is equal to 0 and r is equal to 1. D theta. Then 2 over 3, and did I move that out? Oh, I did. Okay, so we can move this 2 over 3 out. We can first multiply or cross multiply these two, or I guess just multiply these as a fraction. You get 2 over 48, which would be 1 over 24, and then 1 over 24 times 1 over 3 would give you 1 over 72. Yes, 1 over 72. Yes, so 1 over 72, and then we'd be evaluating this, moving it out. So then we would get, yeah, that sounds about right. So if we evaluate at 1, we then have the following. So we have 1 plus 1 squared, so 2 to the 3 over 2. Minus, and then when you plug in 0 here, this is where you do want to be careful. This is where I also remember making a lot of mistakes during whenever I was doing practice. Forgetting to substitute 0 in, because in this case, when you plug in 0 over here, you actually get 1 to the 3 over 2, but that's just still 1. And then now we effectively are left with just this part of the integral. So we've kind of evaluated that, and there's just a 1 in the integrand, or as the integrand. So you just have theta evaluated at evaluated by going from 0 to 2 pi, which is obviously just 2 pi. So in this case, you would have a 2 pi over here, or just pi over 36. And then 2 to the 3 over 2, minus 1. And this is your final answer. Question 6, we want to find the extreme values of f of x, y, z is equal to xz plus xy, subject to these constraints. So of course, this is a Lagrange multipliers question. We are looking for extreme values, and we have our two constraint functions. So first, we need to find the gradients of each of these functions here, and of course, we'll label g and h accordingly here. So we'll do that first. So we have let g of x, y, z we're just setting this equal to the variable portion of the constraint function of xy, and then we also have h, so h of x, y, z, and this is just equal to x squared plus z squared. And then next we need to then set up a system of equations that we will eventually solve. So let's say we need to solve the following system. So the system we have is right over here. So you have the gradient of f, and it's equal to lambda, which is just a scalar multiple, times the gradient of g plus mu times, did I say delta? I don't know if I said delta or not, but the gradient of h here as well. And then next we just have the two constraint functions. So we have xy is equal to 1, and then we have x squared plus z squared is equal to 2. So our goal is effectively to solve this system of equations. This right here gives us two quantities or two equations. This right here, although it is just one equation, it does give us three equalities because each of these we can equate component-wise because these are indeed vector functions. So let's compute each of them. We have the gradient of f here. And remember, the gradient is just taking the partial derivatives of each component with respect to x, y, and z, just for each component slot. So first is f sub x. So partial f, partial x. X is a variable, so these two are basically just, so just z plus y. Next, we have just partial f, partial y. So y is a variable. This goes to 0. All we have left over is x. And then same thing for the z components, because in this case, this goes to 0, and then all that's left over here is just this x term. Next, we have the gradient of g, which can be found using just the exact same way. So this is our function g right over here. We're taking the derivative with respect to x first, so x is a variable. We at least have y. and then vice versa for, x is a variable, so we just have y, and then y is a variable, so we just have x. And then since z doesn't appear, let's just equal to 0. Y x 0, yep. And then finally we need the gradient of h. Which again, h is this function over here, so partial h partial x is just 2x. Y doesn't appear, so it's 0. And then we just have 2z for the z component. Wow, one more try. Good enough. Okay. So now that we have these three expressions over here, we can use this equality over here to equate them. And this gives us the following 5 equations. So first, we can equate the x components, or just the first components of each of these. So we get z plus y. And again, remember, we're multiplying the gradient of g and h by lambda and mu, respectively. So we have y times mu, or just mu, I think. Lambda y plus, and then we have mu times the x components, so 2 mu x. No, that's lambda 2 mu x. Second equation, we can equate this, and the 0. But the 0, again, just cancels out the, or doesn't cancel, but just multiplies the 0 with the constant mu as well, so that doesn't appear. So what we just have here is x is equal to lambda x. And finally for 3, we can equate this, and this. Again, notice we have a 0 here, so lambda will end up here. And then we're just multiplying 2z by mu. So we have x is equal to 2 mu z. And then finally 4 and 5 are just the constraint functions themselves. So we have xy is equal to 1. And then we have x squared plus z squared is equal to 2. Okay, so over here on the side, we'll quickly do it. I'll do it in this portion here just so it's a bit more clear. So first we can take a look at number 2. I guess I'll write it here. So number 2. So from 2, we notice that we have x is equal to lambda x. If we subtract the lambda x to the other side, we then get x, and then we can factor. So we have x times 1 minus lambda is equal to 0. Meaning we can then solve for x using the 0 product rule. We know that, or x and lambda, so we know that x is either equal to 0 or lambda is equal to 1. However, in this case, if we take a look at number 4, we have that x times y has to equal to 1, meaning there's no way for x to equal to 0, because that would obviously give us 0 is equal to 1, which we know that's not true. So here we can say, so since x goes right 4, so 4, x cannot equal to 0, meaning lambda is equal to 1. Okay, so next, if we use lambda is then equal to 1, we can make use of that in equations 1 and then equations 3. So from 1, if we plug in lambda is equal to 1, we effectively just get z plus y is equal to y plus 2 mu x. And here, obviously, the y's would just cancel out. And then we're left with z is equal to 2 mu x. Using this equality now, in conjunction with number 3, we can then solve for the following. So we have z is equal to 2 mu. And then x we're just going to replace with 2 mu z. And then from here we can do some further manipulation. So we can first expand this. So we get z is equal to 4 mu squared z. And then we can move everything to one side. So we then get z times 1 minus 4 mu squared is equal to 0. And then using that exact same idea, we can then further solve here. So continue it over here. So this then tells us that either z is equal to 0 or 1 minus 4 mu squared is equal to 0. In this case here, I think, yeah, it was number 3 that gave us this restriction. So clearly from this exact same idea, we know that x cannot equal to 0 in this case, and that also forces z to be non-zero as well. And in this case, we can then cross this out. So z cannot equal to 0. And then meaning we have this equality here to be true. And if we solve for that, we then get that mu is equal to plus or minus 1 over 2. Yeah, you can do this again just by adding this to the other side, dividing the 4 over, and then taking the square root of both sides. So now we can consider the two cases here. So one case is where mu is positive 1/2, and the other case where mu is negative 1/2. So mu is equal to, I think, 1/2. So if mu is equal to 1/2, we can then take a look at number 3 over here. So I guess I'll just write 3, then gives us that x is equal to 2 times 1/2 z. Obviously these two will cancel out, meaning x is equal to z. And now using this information, we can then take a look at number 5. So then from 5, we can plug this in, and then we get x squared plus x squared is equal to 2. This is obviously the same thing as just x squared is equal to 1, meaning x is equal to plus or minus 1. And then finally, we can come into here using number 4. I guess I can, space-wise, do I have enough? Yeah, I think I will. Did I use number 4? Yeah, I did. Okay. Actually, yeah, here, I'll write this all in one line. And then, so from 4, because x is equal to plus or minus 1, x times y is equal to 1, meaning they have the same sign. So in this case, y is also equal to plus or minus 1. So this is one set using the fact that, or using one case where mu is equal to 1/2. Next, we're going to consider when mu is equal to negative 1/2. Overall, it's pretty much the same thing, just some minor differences. So again, we'll still use 3, except in this case, we have x is equal to 2 times negative 1/2 times z, meaning x is equal to negative z instead. I guess in this case here, I should also, let's write that. We also get that z is equal to plus or minus 1, because again, z is equal to x. However, in this case, we have this equality instead, which we'll see changes the answer slightly. So using the fact that x is equal to negative z, we can still use 5 in the exact same way. Or again, x squared plus x squared. Simply again because if we, or I guess it's the same thing as z is equal to negative x. And then once you substitute that into here, you still get the same result because it's being squared. So this is equal to 2. And then this also tells us x is equal to plus or minus 1. And then again from 4, we also get that y is equal to plus or minus 1. However, the minor change now is that because x is equal to negative z, we then get that z is equal to the opposite of this, which is, I guess, minus plus. I'm not sure if that's actually the notation used, but regardless, it has the opposite sign now. So from here, we can then conclude that the possible points, so therefore the possible points for Extrema are as follows. So we'll start with positive 1/2 for mu. We have when they're all positive or when they're all negative. So yeah, so 1, 1, 1, negative 1, negative 1, negative 1. Yeah, I'll fit. Actually, let's see if I can fit. Actually, no, I probably can't. That's fine. So that's from the first option over here. Second option here, it's basically the exact same thing. We keep in, except we keep in mind that x and y are the same. Z has to be opposite. So we have 1, 1, negative 1. We're at the end here. And then we have -1, -1, 1, I believe. Yeah. From here, we can then evaluate our function f at each of these points, and then we can compare the points. So f of 1, 1, 1. If we just plug it into this equation right over here, it just becomes 1 plus 1, which is 2. And then we also have f of -1, -1, -1, which should also be 2, I believe. You have -1 times -1 plus -1 times -1, so it's again 1 plus 1. I guess the right column is here. And then f of 1, 1, -1. In this case here, I think we get 0 instead. So we go 1 times -1 plus 1 times 1. So we should get 0, I believe. Yeah. And then the last one will also be 0. F of -1, -1, 1. This is also equal to 0. So from here, we can then finally conclude that the maximum is at, what do we claim here? Yeah, 1, 1, 1. And -1, -1, -1. And the minimum is at, and we'll write the following 2 points down here. So we have 1, 1, -1, and -1, -1, 1. I believe just ask for the value. Or I guess, yeah, and we can say the values are the max value is 2, and the min value is 0. Question 7, we want to evaluate this triple integral where E is a solid bounded by the cylinder x squared plus z squared is equal to 1, and the plane x plus y is equal to 1 in the first octant. So the first octant, again, is just bounded by the planes x is equal to 0, y is equal to 0, z is equal to 0. It's kind of the positive portion of the 3D space. So let's get into this. First, we definitely want to sketch a picture first. So let's do that over here on the side. And because we're only dealing with the first octant, I only really need to draw that much to kind of represent that space. These arrows look ugly. Okay, so this is your x, y, and z. Oops. Okay. So first we can, I guess, yeah, it'd be easy to sketch this part first. So you can imagine what this looks like in just the xy plane, the flat Cartesian plane. It's just y is equal to 1 minus x, but regardless, we'll do it an easier way. You can see when x is equal to 0, y is equal to 1. So let's say over here roughly. And then vice versa, whenever y is equal to 0, x is also equal to 1. So somewhere over here, let's say. So it's 1. And then we can draw a straight line across. Let's do that better. Okay, and yeah, I'll quickly shade this part in. Okay, and yeah, I'll specify this as x plus y is equal to 1. Next, we can sketch this part over here. We have the cylinder x squared plus z squared is equal to 1. So this, what you want to visualize, is quite literally like your actual conception of a cylinder, like a can shape that basically runs along this way. So it kind of looks something like this. But obviously it extends infinitely both ways, and effectively that's kind of being cut off by the x is equal to 0, y is equal to 0, and z is equal to 0 plane. So yeah, this is what this would look like. So like, yeah, y is equal to 0, but obviously we would have something like this if we just take these points here. So if x is equal to 0, we have, if x is equal to 0, z is equal to 1. So somewhere up here, I'm going to try to sketch it a bit more accurately. So 1 roughly right over there. And then obviously when z is equal to 0, x is also equal to 1. So you can kind of imagine what this actually looks like. It's quite literally just a massive circle, but obviously, again, it just goes both ways infinitely. But for the portion we're concerned with, which is, again, in the first octant, it looks something like this. Yeah, that's good enough. And then, let's see. Yeah, this portion here, it's kind of cut off. We'll roughly draw it like this. Okay, yeah, we won't shade it in per se, but that's fine. And then, again, this line over here, you can also imagine that kind of cylinder being chopped kind of by like a string. Yeah, I definitely can't do it with my hands. But you can imagine that cylinder being chopped by kind of like a flat, straight diagonal plane, which would kind of give this kind of effect here. Oh, that's a bit flatter. Yeah, something along these lines. So this is roughly what the solid will look like. And then we'll also draw the projection into the plane as well. And yeah, I'll specify that this here is x squared plus z squared is equal to 2, or is equal to 1. Yeah, equal to 1. And then we can then draw the projection. So, and yeah, I'll also specify this is a solid E. Okay, so we'll draw the projection into the of this entire solid into the in the xy plane. So in the xy plane, again, we're now just looking at the flat 2D Cartesian plane. So something like this, and then we of course have our x and y. This is the only thing we're really sketching, and again, we can kind of solve for y. We just get y is equal to 1 minus x. So we know the slope of -1, and our y-intercept is just 1 as well. So let's say we draw 1 over there. And then just a diagonal line straight down, roughly, that's a point. This is 1 as well. So again, if you solve, this is y is equal to 1 minus x. Then, yeah, we can briefly sketch this in as well. Okay, nice. From here, we can then quantify this one or find basically a way to use intervals to describe it. In this case here, we can bound this between x, so x goes between 0 and 1. And then y goes between y is equal to 0 and this line over here. So it effectively starts here and goes up to this line here. So y goes between 0 and 1 minus x. And this right here describes the projection into the xy plane. So we're effectively going to view this 3D solid as a type 1 region, a type 1 3D solid, which again basically tells you that we're looking to project it into the xy plane, and then the solid will be bounded between two functions of z in terms of x and y. Okay, so yeah, to proceed with that, we then need to, of course, solve for this function here in terms of, or for z in terms of x. So we have x squared plus z squared is equal to 1. And then now we can further solve for z. So z squared is equal to 1 minus x squared, which then gives you that z is equal to plus or minus 1 minus x squared, all square rooted. Okay, with this in mind, we're obviously just going to use the positive one though, because we are dealing with the first quadrant. So yeah, let's get rid of that. But usually it's best to keep in mind that there is the positive and negative. From there, we can now actually set up the triple integral. I'm just going to quickly write out the z boundaries for the solid over here. So z, it goes between this bottom part over here, which is just z is equal to 0. So we have 0 is less than or equal to z. And then obviously the top portion over here is this right over here. So if we were dealing with the bottom portion, the negative would come into play to describe the bottom portion here below z is equal to 0, but obviously we're not dealing with that. So we just have 1 minus x squared square root. Just like that. Okay, and now we can actually set up the triple integral. So we have the triple integral over the solid E of the function z and then dv. And then now we can actually set up the integral properly. So notice that we are going between, or we have, this is our 2D projection into the xy plane. This is our z. We're going to be evaluating that first on the inside, and then we're going to slowly work our way outside. So on the outside, we're going to have this. And because this is a, I believe, type 1, but for 2D regions, we're going to have x then y. I believe so, x and y. Yeah, so x on the outside, y on the inside. So it's going to be dy dx, but then on the inside we have dz. So dz, dy, dx. So x on the very outside, x goes between 0 and 1. Y goes between 0 and 1 minus x. And then z goes between 0 and 1 minus x squared. Square rooted, I believe, yes. And then just z, and then dz, dy, dx. Notice that, again, these here will match up, these here will match up, and this right here will also match up. Typically, you might see this kind of written as this. You're technically evaluating that inside integral first, and then you're kind of appending on the little outer integral. Okay, let's evaluate this now. So we can rewrite this. So integral between 0 and 1, 0 and 1 minus x. Z, we can directly take the integral. It's just 1/2 z squared. This is being evaluated at 0 and square root 1 minus x squared. Dy dx. The 1/2 we can just move to the outside, I believe. Yes, we just move it to the outside. So 1/2 times the integral between 0 and 1. Then the integral between 0 and 1 minus x. Z squared evaluated at this is simply just this portion, because 0 squared is still 0. So we just have 1 minus x squared. And then dy dx. Of course, because y doesn't really appear here, we simply just have 1 minus x squared times y, evaluated at 0 and 1 minus x. This part is unnecessary, but I'm just writing out all the steps. Effectively, you're kind of moving this out using the fact that you have an iterated integral, because again, y doesn't appear here, so you effectively just have a constant, which again, you take the integral of, you just have y. And in this case, you then just get 1/2 times the integral between 0 and 1 of 1 minus x squared times 1 minus x dx. And then now we can expand this inner binomial being multiplied. So we have 1 minus x squared minus x plus x cubed, I believe. Yep. Dx, and then I'm just going to rewrite this really quickly just so it's ordered nicely. So we have x cubed minus x squared minus x plus 1. And now this is something simple that we can directly integrate. So we'll do that. So we have 1/2 times the following, so 1/4 x to the 4 minus 1/3 x cubed minus 1/2 x squared plus x. This is all evaluated for between 0 and 1. So then here, of course, every single term here has an x in it, so the 0 is irrelevant. We're just plugging in 1 everywhere here, so we have 1/2 times 1/4 minus 1/3 minus 1/2 plus 1. Here, the least common multiple would be 12. So with 12, you effectively, what do you have? You have 3 over 12 minus 4 over 12 minus 6 over 12 plus 12 over 12. So in this case, you have -1, -7, -7, and 5. So you have 5 over 24, yeah. And then you have 5 over 24 in this case. Yeah, you don't have a calculator on these finals, so definitely make sure you are able to add fractions. Hopefully you are by now, but yeah, that's how we get this answer right over here. Question 8, we want to... Question 8, let f of xy, a vector function, equal to e to the x ln y minus e to the y over x, comma y plus e to the x over y minus e to the y ln x, and let c be the curve parameterized by r of t is equal to t, comma t cos of t over 3 for t between 1 and pi. So first we want to see or determine if f is conservative. Remember, the easy way to do this is to check the partial derivatives of f, the components. So we can just label these as p and q really quickly. So yeah, let's check that really quickly. So we know that f is, let's write it out again, so it's conservative if and only if partial p is partial p partial y, yeah, partial p partial y is equal to partial q partial x. And yeah, I believe one of the videos I have goes over why this is the case, but it's basically a matter of setting these these equal to and setting it up equal to the gradient of f, which is kind of the definition of conservative. Again, vector field is conservative if there is a potential function, the potential function gradient of f. But yeah, okay. So because we have this, we can simply compute partial p partial y and partial q partial x and see if they're equal. So partial p partial y is equal to the following. Y is a variable, so this part here, e to the x, is just a constant effectively, so we have e to the x over y minus, and then e to the partial p partial y. So y is a variable, so e to the y over x. And then, yeah, that's enough space. So, and then we have partial q partial x. So the same idea, y goes to 0. We have e to the x over y. And then, again, x is a variable here, so we just take the derivative of that. So minus e to the y over x. And then notice that partial p partial y and partial q partial x are indeed equal, hence we have this. And then we can just conclude, so therefore, since the partials are equal, we have that f is conservative. Okay, so that's this part. Next part, we want to evaluate the line integral. Just the typical line integral over c. The point of this question is to use FTC for line integrals. You'll notice later on, I'll mention it again, but if you were to do this directly, just using the definition of like this, a to b, f of r of t times r prime of t dt, and then you try to evaluate, you're not going to have a fun time. But because we know it's conservative, we are able to employ FTC for line integrals, and it makes our lives a lot easier. The only issue with that is we need to find a potential function first, so let's do that. So we have, I'll quickly state it, I guess. So the line integral over c of a potential function or a conservative function, or conservative vector field, this dot dr is equal to f evaluated at r, so r of a, or r of b, sorry, minus f of r of a. And then this is where t is between a and b. And again, this all kind of alludes to the fact that we need a potential function. So need potential function. Okay, so yeah, this is again the main idea. We indeed are still evaluating the same thing because f is conservative, we can find a potential function, the gradient of f, and yeah, and then again it's equivalent to this. So let's get into that. So first we have, so let's write out the equality. This is equal to vector f. Our entire kind of main thing is predicated off of this. Okay, so this implies the following. Remember that gradient f is just equal to f sub x comma f sub y. And we know what f is equal to. It's literally just equal to this up over here. So this gives us the following. So one, we know that f sub x has to equal to p, so e to the x ln y. E to the x ln y minus e to the y over x. And then 2, we have, I guess we're and, let's write and here. So and then 2, we have that f sub y must equal to this function here. So y plus e to the x over y. E to the x over y, and then minus e to the y ln x. On x. Okay. So with this, we have choice. We can either work with this or we can work with this. So 1 or 2. It doesn't really matter. Usually it's just convenient to go with the first one. Again, it really doesn't matter. So let's do that. I'm going to write f sub x in terms of like the partial notation, just so it's a little easier to digest. So we have partial f, partial x. And we know this is equal to this right over here. So e to the x ln y minus e to the y x over x. From here, we're going to integrate both sides with respect to x. So that's kind of the big step we're doing over here. There's really no other way to think about it other than you're just integrating both sides, but with respect to x only. So you integrate with respect to x, and as usual, whenever you're doing partials or with respect to something, you just treat that one thing as a variable, everything else is a constant. So in this case, we then get that f is equal to, I'm not going to write the integral of all this, but you get the idea. We're just integrating this with respect to x. So we just get e to the x ln y. And then minus here, we just basically effectively have negative e to the y times 1 over x. Derivative of y is equal to 1 over x, it's ln x. So we have minus e to the y ln x, I believe. Yeah. And then instead of an integration constant, we need to add a constant function in terms of, it's a function of the other variable that we're integrating with respect to. So we're integrating with respect to x here. We have to add some function. I think I called it h, or I called it g. So let's call it g of y. The reason for this is because we have a variable y, we don't necessarily know that whatever the constant is, we don't know if it's a numerical value or if it is a variable or some function in terms of y. If we were to take the partial derivative of both sides with respect to x, we still get back to this exact function here, so that's totally fine. But yeah. Okay, so we currently have this expression over here for f. Now our goal is to solve for whatever g of y is. We need to solve for that constant so we can actually solve for what f is equal to. So in this case, we can make use of the second equation now. So let me see, I'll mark this down here. So we're effectively just using what we just solved for there inside of 2. So we know that, again, partial f partial y is just equal to the other equality we had there. So y plus e to the x over y minus e to the y ln x. However, we can make use of this right over here. We have this expression for f over here, but we can still take the partial derivative of this with respect to y as well. And this is kind of where the magic happens. So we're going to replace this with the partial derivative of this expression for f, but again, taking the derivative of it with respect to y. So we have e to the x, and then ln y, derivative of that with respect to y is just y. Then this stays the same, e to the y ln x. Here, this is where it's important that we just don't have a constant, because we take the derivative with respect to y here. If this was a constant c, it just goes to 0, except in this case, it goes to g prime instead. So you have g prime of y. And this is still equal to that exact right side, so y plus e to the x over y minus e to the y ln x. And then from here, we can then isolate for g prime of y and then integrate once more to isolate for whatever that is. So here, notice that we can cancel some things out. Negative e to the y ln x, negative y e to the ln x, e to the y over, e to the x over y, and e to the x over y. So what we're ultimately left with here is g prime of y is equal to y, and then now we can integrate both sides to get that g of y is, g of y is equal to 1/2 y squared. In this case, this is where you would want to put a constant c, but because we usually just take the c to be 0, it really isn't too relevant, so we can just omit it for now. I definitely took a little more space than I intended to, but it's fine. Okay, and then we can then finally conclude. We can finally now conclude that our function f, using this expression here, combined with this right over here, is equal to e to the x ln y, e to the x ln y minus e to the y ln x, and then plus g of y, which is just plus 1/2 y squared. Now, we can actually get back to evaluating this right over here. So we can then conclude the following. Integral over c of our vector function f, or vector field f, dot dr. This is first of all equal to the line integral over c of the gradient of f, dotted with dr. And then now we're making use of FTC for line integrals. So this is equal to f of, again, our AB is actually given to us right over here. So we start at 1 and at pi. So pi is kind of our B, 1 is our A. So we have f of r, I believe we have r of pi, minus f of r of 1. Okay. R of pi, we can evaluate here really quickly. So if we put pi here, we have pi, comma, pi times cosine of pi over 3. Cos pi over 3. Yeah. And yeah, we can write that down here. So this is equal to, how did I write this? Okay, yeah, so f of pi, comma, pi times cos of pi over 3 minus f of 1, comma, and this is just 1 times cos of 1 over 3. And we can simplify this one step further, so pi, comma, and then pi times, so this is cos of pi over 3, which is cos 60, so 1/2, I believe. Yes, 1/2. So we have pi over 2. And then just minus f of 1, comma, 1 times cos of 1 over 3 is just cos of 1 over 3. And I'm pretty sure this is how the instructors left their response. You can definitely evaluate these two, but you just get some pretty messy expression. Regardless, it does speak towards why you would want to use FTC for line integrals. rather than directly evaluating using the definition, which gets a lot messier. Yeah, that's how we do this question over here. Question 9, we want to evaluate the following surface integral, where our function is just equal to 1, 1, 1. S is this part of the sphere in the first octant, and we have n being the unit normal of the surface S. So first, we'll know that this right over here, let's see if we can curve it a bit. There we go. This is simply a sphere of radius 2. And again, we're dealing with the first octant, so we can do a quick sketch of this right here. Of x, y, and z. And because it's a sphere, it's much easier to sketch, especially because we're only limiting ourselves to the first quadrant. So yeah, in this case, we can pretend, yeah, if x and y are both equal to 0, so along the z-axis, we have z squared is equal to 4, means either equal to positive or negative 2. But because we're dealing with the first quadrant, we know it's equal to 2. And then using that exact same logic, we can compute this. We'll realize that's 2 for x and y as well. So I draw a diagonal line just to get the 2 to be roughly on point. So 2 over there. And then, unfortunately, here it's going to be a bit of a guess. Yeah, it looks about right. So 2 there. And now we can finally draw the sphere part. Let's see if we can get it a little more round. It's a little too round. That'll have to do. In retrospect, that looks a little too far. We'll just go with that actually. So let's hit 2 right over there, and then finally over here, we can draw this right over here. Nice. And this, or actually, I guess that shading works, but the idea is we have our solid right over there. Okay, so first I'll quickly write out the formula that'll help us compute this, and it involves having to parameterize the surface. So instead of parameterizing a curve using one variable, so you'd represent a 2D curve using one variable, we can parameterize a surface using a surface in 3D using 2 variables. So in this case, we have the following. So the surface integral over the surface S f dot n ds. A common other notation you'll see is just this being written as something like this. They both mean the exact same thing. Anyways, so this right here is equal to the double integral over a region D, which I'll explain in a second. So f dotted with the parameterization of our surface in terms of, or the partials, and then their cross product, basically. So in this case, usually you'd use u and v, but I'll kind of skip ahead. We're basically going to eventually use phi and theta instead, so spherical coordinates. So we have r sub phi, or the partial derivative of r with respect to phi. And we're crossing this with, I'll draw that again, crossing it with r sub theta. And then I believe dA, yeah. So D is simply the parameter's domain. So D is the parameter domain. Meaning we're basically just going to have a region, our region D, that is created from parameterizing the sphere of radius 2. But yeah, so we'll use spherical coordinates here. So spherical coordinates. spherical coordinates. Okay, and then yeah, so the way we usually do it is we'll somehow want to get rid of one of the variables or kind of have them on their own. This again is a sphere of radius 2, and if you recall the conversion, or I guess the change of variables, like the formulas, we know that one of the variables can effectively be eliminated. So normally in spherical coordinates we have rho phi theta, but in this case rho is a constant, right? So we're only left with two variables. So in this case rho is equal to 2, or effectively rho is held constant. So instead now we have x is equal to, so x is usually equal to rho sine phi cos theta, but in this case rho is fixed to be 2, so we then have 2 sine phi sine phi cos theta. Y is equal to 2, the same, so 2 sine phi sine theta. And our z, or z, is simply equal to, again, normally it's equal to rho cos phi, but in this case it's just 2 cos phi. I have this right over here. And then finally we can also write out the parameterization, or the domain of this. Let me move this over a bit. So in this case, again, rho is fixed, so we're only looking at phi and theta. If we look at our shape over here, phi, remember, it kind of opens up from this side and we're kind of opening downwards. So in this case, it starts from here, ends down over here. This is a 90-degree angle. So phi goes between 0 and 90. Or 90, or just pi over 2. And then theta, on the other hand, exact same idea. It's kind of our circular angle. And in that case, it's just also equal to, or it goes between 0 and pi over 2 as well, because we're only traversing through this portion over here. So 0, theta, pi over 2. And now we're ready to fully write our parameterization. So remember, the parameterization is usually something along these lines. So uv, y of uv, z of uv. In this case, u and v, it really doesn't matter what they are. In this case, I simply just picked our spherical coordinate variables, phi and theta. So let's write that out over here. So R, again, we're just copying this basically right over here in terms of a parameterized kind of surface. So 2, oops. So you have 2 sine phi, 2 sine phi cos theta. And then we have 2 sine phi sine theta. And then finally, we just have 2 cos phi. And that is our parameterized surface right over there. So next, if we take a look at our equation over here, we need to find the partials of this with respect to phi and theta. So we'll compute that right down here. Yeah, so sub phi. So again, partial derivative of this is just the partial derivative component-wise. So in this case, we have 2, and then sine phi becomes cos phi. 2 cos phi cos theta. And then we have 2 cos phi sine theta. And then we have negative 2 sine phi, I believe. Yes. Okay. And then next we need to compute the partial of r with respect to theta. So r sub theta. Slightly different. In this case we have negative 2 sine phi and then sine theta. Oops. So just the derivative of cos theta, which is negative sine theta. So sine theta, and then yeah, same idea here, except this is now 2 sine phi cos theta. And then in this last component over here, we notice that theta doesn't appear at all, so we simply just have a 0 here. Just making sure that's correct. Yeah, and we're good to there. Okay, and then next we want to find the cross product. So if you've watched any of my other videos, you'll know that there is a much easier way to compute the cross products, or easier depending on how you want to see it. The traditional way is to set up a 3x3 determinant with I, J, K, and then your two functions. But I find this to be it's quite literally exactly that, except no thinking involved, and you don't really have to match things up either. All you have to do is simply write out both vectors. So one vector, and then repeat it beside itself. Right below it, write the other vector and repeat itself. So I'll quickly write that out right over here. So we have 2 cos phi cos theta, and then 2 cos phi sine theta, and then -2 sine phi. Okay, and this time I won't abuse my iPad privileges. I'll just write it out entirely. So here again we repeat. So we have 2 cos phi cos theta, 2 cos phi cos theta, then 2 cos phi sine theta, and then -2 sine phi. Right, so this is simply just the first vector we're crossing, written out twice beside each other with some space in between. And then next we'll just copy this and do the exact same thing. So -2 sine phi sine theta, two sine phi cos theta, then 0. And then we repeat the exact same thing. So -2 sine phi sine theta, 2 sine phi cos theta, and then 0. So after we've done this, we can cross out the far left and far right, and then now we can just kind of crisscross to find each component of the cross product. So we'll write it down over here. So r phi cross with r sub theta, it's then equal to the following. So this times this is equal to 0. So you have 0 minus this times this. This right here is negative, so it just becomes the positive of it. So we have effectively positive 2 sine phi times this, which gives us 4 sine squared phi cos theta. So that's this times this minus that times that. Next, we repeat with just these two instead. The two negatives will cancel out. So we have 4 and then sine squared phi sine theta. Normally here we would subtract, but again we're multiplying by 0 here, so it just it just goes to nothing. And then lastly, this one is a little chunkier, but you'll notice that it actually is pretty convenient to work with. So we have 2 cos phi cos theta times 2 sine phi cos theta. So we have 4 cos phi, or I'll write sine first, so 4 sine phi cos phi, let me see, 4 sine phi cos phi, and then cos squared theta, minus, here again same idea, we have a negative, so it actually becomes plus, so plus, and 4 sine phi cos phi, and then a sine squared, so cos phi, and then sine squared theta, and that's that. Alright, so no need to write the entire 3x3 determinant, kind of compute it part by part, blocking off one row and everything. I think this is far more direct. But yeah. This, we're actually going to make a quick simplification here. So notice that if we factor out 4 sine phi cos theta, we're left with this times cos squared theta plus sine squared theta, which is obviously just equal to 1. So we're actually just left with this portion over here. And that is the cross product. Okay, so if you take a look now, we have f, obviously it's just right over here, and we've computed this. So now we can actually move on to computing the integral. Or sorry, one last step. We actually have to compute the dot product between these two, but it's quite simple because f is simply just equal to 1, 1, 1. So we'll write that over here. So f dotted with r sub phi cross with r sub theta. Yeah, it's just equal to this part. I will copy and paste just for convenience sake. It's just this dotted with this vector over here. And in this case, you'll notice that we're just basically adding each of these component-wise. So we have the following. Actually, yeah. So before I go on, notice we can just factor out the 4, and then we'll have each of these on the inside being added. So we have 4 times, and then sine squared phi cos theta, plus sine squared phi sine theta, and then sine phi cos phi. Let's make sure we're good up to this point, and we are. Okay, now we can actually make use of this and compute. So we can then conclude, therefore, the double integral, or not the other, sorry, the surface integral over our surface S here of f dot n ds is equal to the following. So again, we're integrating this function here effectively, so we can pull out the 4 first. And then now we can actually set up the double integral. So again, remember our domain D is basically just the parameter domain, which is right over here. And remember with spherical coordinates, we usually go d rho, d phi, d theta. So we'll go in the same order. So d phi, d theta. In this case, it doesn't really matter because both are between 0 and 1/2. Sorry, pi over 2. But yeah, d rho, d phi, d theta. So theta is on the outside. So 0, pi over 2, 0, pi over 2. And then our function right over here. So sine squared phi cos theta plus sine squared phi sine theta plus sine phi and cos phi. And again, d rho, d phi, d theta. So d phi, d theta. Okay. Yeah, I guess I'll also add this. So a lot of times you'll see this added, like a square bracket here, added for clarity. This is one of those things that you have to make sure to clarify with your instructor, whether they actually care about this or not. I've seen a video of some other prof on YouTube actually saying that she'll deduct marks if you don't include these brackets. But the teaching team or the TAs that were grading, they weren't that harsh on this. Or sorry, they weren't harsh at all. They didn't really care. But yeah, this is kind of the more thorough notation, I suppose. Okay, so what we'll now do is, let me see. That's how we integrated, okay. I want to see what the easiest way to explain this is. Okay. I swore I actually wrote it out a lot more. Okay, I guess I didn't. I'll write it out longer here, just so it's super, super clear. But effectively, this right here is the same thing as integrating each of these separately and then adding them together. So yeah, I'll just do that really quickly. Actually, I probably won't have space. Yeah, if that is confusing, please do leave a comment if anyone does make it to this point. But yeah, we'll proceed with the following. So we have 4. And then here. So for this right over here, if you imagine this here, d phi, d theta, we can basically write this as an iterated integral because they're being multiplied. One is going to be held constant when we're integrating with respect to phi anyways. So we can actually rewrite it as the following. So 0 pi over 2 sine squared phi d phi. And then times the integral from 0 to pi over 2 cos theta d theta plus the integral from 0 to pi over 2 sine squared phi times, or I guess, yeah, d phi, times the integral from 0 to pi over 2 of sine theta instead in this case, d theta, plus the integral from 0 to pi over 2 of, and then sine phi, sine theta, I guess. Yeah, so sine phi, sine phi cos phi. So sine phi cos phi d phi. And then finally, we're just going to add the integral from 0 to pi over 2. Just 1 d theta. We're going to close it off. Yeah, I'm definitely writing bigger here now for some reason, but that's fine. Okay, so now we can evaluate each of these individually. This right here is a really common integrand that you will see, sine squared phi or sine squared of something. I'll quickly write on, I guess, this side over here. It's a bit squished, that's fine. So we'll use the fact that we have, or we use the cosine double angle identity. So cos of 2x is equal to 1 minus 2 sine squared x. And then if we isolate for sine squared x, we get that sine squared x is just equal to 1/2 times, 1 minus cos 2x. Cos 2x, yep. And then we'll quickly just integrate this over here so we can kind of use that repeatedly. So the integral from 0 to pi over 2. That 1/2 will move to the outside, and then we have 1 minus cos 2x dx. I'll write it over here. It's getting a little squished, but that's fine. So it's 1/2. Here we can just directly integrate. So 1 just goes to not theta, but x. And then you kind of ask yourself, derivative of what is equal to cos of 2x, derivative of sine. So then we just have to multiply by the 1/2 here to account for, the 2x inside. And then evaluate it from 0 to pi over 2. Again, you can take the derivative of this. You get negative 1/2, and then cos 2x times 2. These two will cancel out, and you're just left with this again. Evaluating here, the 0 obviously doesn't contribute anything. It'll go to 0 both ways. So you basically just have 1/2 times pi over 2. Here, though, as well, sine of 2x is sine times pi over, sine of 2 times pi over 2 is sine of pi, which if we go over all the way here, sine is 0. So it ends up just being this, which is equal to pi over 4. So we'll make use of this. We know that this right here then is just pi over 4. Same with this. This is just pi over 4. Okay, and then this right here we can just quickly evaluate without having to write it out. Derivative of what is equal to cosine, derivative of sine. Derivative of sine is cos, and then sine evaluated from pi over 2 to 0. It's just sine of pi over 2, sine 90, which is 1, minus sine of 0, which is 0. So this is just 1. And then I want to say same idea here. In this case, derivative of what is equal to sine theta, it's negative cos theta. Negative cos theta, you evaluate from from pi over 2, from 0 to pi over 2. So you get negative times cos of pi over 2, which is cos 90, which is 0, minus, and then cos of 0, which is 1. So you get negative times negative 1, so this is also 1. And then this right here, did I have to do this on the side? I guess I quickly wrote it on the side. This I'll do over here. So actually, here, I can move this up a bit so we can fit it all on the side here. So sine phi, cos phi, or sine x cos x, it's pretty clear that it's just equal to, or the derivative of it. Right here, let's write it out here. So integral 0 pi over 2, sine x cos x dx. We're just seeing the derivative of what is equal to this. Hopefully you recognize that it can just be 1/2 sine squared x. Let's write that here. So 1/2 sine squared x evaluated at 0 to pi over 2. Again, this is because if we take the derivative of this, we get 1/2 times and then 2 sine x times derivative of the inside, which is just cos x. These two cancel out, which again gives you that. And then this evaluated at 0 and pi over 2, so sine 90 is 1, sine pi over 2 is 1. So in this case, this ends up just being 1/2. This right over here, obviously it's just theta evaluated from pi over 2 for 0 to pi over 2, so this is just pi over 2 as well. Okay, and then this is what we then get. So we get 4 times the following. Pi over 4 times 1 is pi over 4. Pi over 4 times 1, again pi over 4. And then 1/2 times pi over 2, pi over 4. So these obviously will all cancel out, and you're just left with pi plus pi plus pi, which just ends up being 3 pi. And yeah, that's how we do this question. Question 10, evaluate the line integral where f of xy is equal to this function here, x cubed y squared, e to the x squared plus x to the 4y, and c is the ellipse x squared plus 3y squared is equal to 1 in the xy plane oriented counterclockwise. So I'm just going to quickly preface this by saying I'm not quite sure what the orientation here really has, like what role it plays in this question. My best guess is that it makes it more difficult to actually find a parameterization for the curve C, which kind of forces you to use Green's theorem, which is what they want you to use in this question. So first, I'll quickly just label this as P and Q. And before writing out Green's theorem, I'll quickly sketch out this ellipse over here. Okay, so yeah, I already know it's going to be more of like an oval-shaped ellipse that's kind of squished down in the y direction. So I'll try to quickly draw something that's relatively representative of that. Yeah, slightly off, but good enough. Okay, so yeah, I guess we'll label x and y here as well. So x and y. In this case, we can check. So along the x-axis, we have y is equal to 0. So when y is equal to 0, x is equal to plus or minus 1. So that's how we know we have 1 and -1 here. When x is equal to 0, we have our y-axis, and then y is equal to plus or minus 1 over root 3. So we're just going to pretend that this is 1 over root 3, and this is -1 over root 3. So again, this is our curve C. And we're told that it's oriented counterclockwise. So clockwise would go this way, counterclockwise is just the other way around. So something like this. Okay, next I'll quickly write out Green's theorem, which is what we'll use. Is it Green's? No, just Green. So Green's theorem states the following. So it tells us or I guess I should quickly explain the notation as well. So let me write it out first. So the line integral, kind of looks like a music note. Yeah, I'll quickly explain. So this basically just means it's oriented clockwise, I believe. Which again makes it weird that it says counterclockwise, but it's either going to show like this or this within that little circle to indicate the kind of direction, counterclockwise or clockwise. Still, it's just a line integral at the end of the day. So Green's theorem basically helps us relate a line integral to a double integral over a region instead. Because again, from the previous explanation, this question is probably going to be quite difficult to do from the definition, which requires us to parameterize our curve C. So this dot dr is equal to the following. So it's the double integral. Good enough. Over the region D, and I'll explain what D is in a sec, of the following function. So I think, partial Q, partial X, minus partial P, partial Y, and then dA. And so in this case, D is simply the region that is enclosed by C. So again, MAT235 isn't that rigorous, so you never really get into the deep whys and meaning behind everything. But in this case, this is our curve C. this right over here is D. It's simply the region that is enclosed by C. Let's quickly write let's write the arrow like this. That's D. Okay. So if we take a look at this, obviously again our goal is to compute this, but Green's theorem allows us to compute an easier double integral instead of computing this directly. Excuse me. So let's compute that. So partial q partial x. This again, yeah, I suppose it does kind of matter the order you label them in, but obviously intuitively alphabetical order. So alphabetical order, so just pq. So partial q partial x, again x is a variable, so you have e to the x squared, so it's just itself times the derivative of the inside. So you get 2x e to the x squared plus 4x cubed y, I believe. Yep. And then partial p partial y. Partial p partial y, yep. So we have 2, and then x cubed y. And then this together, then we can use to compute this. So partial q partial x minus partial p partial y. Notice that this is basically the same as this. They're basically the same term, just a different coefficient. So if we subtract this from this, we just get the following. So 2x e to the x squared, and then plus 2e to the, or sorry, just 2x cubed y, I believe. Yes. Okay. So our next step is we want to somehow describe this region using intervals, using x and y. So one of the easier ways to do it would simply just to be having x bounded between -1 and 1, and then we somehow find a way to represent y in terms of x, which we can do pretty straightforward. Do in a pretty straightforward manner or fashion. So let's do that. So x squared plus 3y squared is equal to 1. Excuse me. So here we can then just isolate for y, or we'll do y squared first. So y squared, we're going to subtract the x squared over and then divide both sides by 3. So 1 minus x squared over 3. I guess I could move everything over a bit. And I'm going to square root both sides, but in this case it's important that we take the positive and negative. So plus or minus, and then x squared minus 3. Well, x squared, not x squared minus 3, x squared over 3. And then square rooted. It's tough, a little bit too small. There we go. And this right here then allows us to describe our region D. So D, we can write as x going between -1 and 1, and then y going between these two functions of x. The positive represents kind of this portion over here. The negative, obviously, the complementary portion down there. So y is then between -1 minus x squared over 3, square rooted, and then just the positive of this. Okay, and then with this in mind, then we can finally compute this right over here. So say therefore, oh nice. So C f dot dr is then equal to the double integral over our region D. And our integrand is this exact function over here, so 2x e to the x squared, e to the x squared plus 2x cubed y d8. Okay, perfect. And then next we can actually expand things out. So here we'll make use of this right over here. So we can rewrite this as the integral between negative 1 and 1. And then this part's going to be a bit messier to write. So 1 minus x squared over 3. And then positive, oops. One minus x squared over 3. And then in this case, we're actually going to do a pretty similar strategy where we kind of split the integral. We're just going to separate it and add them together. It'll make a little more sense right after. So 2x e to the x squared. And then here, again, remember our order is, this is x and this is y, so we have our order as dy dx. dy dx. And then plus. This part I'm just going to copy because it is a headache to write. And then 2x cubed y. And then dy dx. Okay. Next step, we're just going to first evaluate the inner portion of each of these. So in this case, y doesn't appear at all, so we simply just have 2x e to the x squared times, in this case, yeah, again, y doesn't appear, so it's simply this minus this. So we get 2 times just this, so we can move the 4 out over here. And then square root 1 minus x squared, I don't like that, 1 minus x squared over 3, and then dx. Plus the integral from negative 1 to 1. Similar idea here, except now we actually have 2y, but it's kind of convenient in the sense that we just get x cubed here times y squared, evaluated at these 2 points. So yeah, it's y squared evaluated at these 2 points. I'm not going to bother writing out the entire thing. But yeah, you know it's y squared evaluated at these, so you effectively just get 1 minus x squared over 3 plus 1 minus x squared over 3, which ends up just being 2 minus 2x squared over 3. So 2 minus 2x squared over 3 dx. Okay. Let me just make sure. That's fine. I could have been a step or 2. That's fine. Okay. So the idea is from this step now, we can find a way to justify that because we're going between negative 1 and 1, and these two are odd functions, we can simply claim that these are both just equal to 0. Feels a bit hand-wavy to me. I haven't quite found a convincing justification as to why this is the case, but these are clearly a slight bit too nasty to evaluate for my liking for now as well. So we'll just, I guess, trust the instructors on this one. So in this case, we can, so claim that this is odd, and this is odd. Hence, this is just 0 plus 0, which is equal to 0. So apologies if that's a bit hand-wavy. On the actual exam, the question we got was far more reasonable in terms of being able to actually take the integral and everything. But usually if you see something between negative 1 and 1, and it's some semblance of an odd function, it's almost always safe to assume that it is just equal to 0 because it's an odd function. But yeah, that's how we do this question. Question 11, we want to evaluate the following surface integral where f of x, y, z is equal to this vector field over here, and S is the part of this sphere over here. I'll again quickly note that this is a sphere of radius root 2. It's not too important, but maybe it is. Sphere of radius 2. It's a sphere of radius 2. Oh, sorry, root 2, my bad. Root 2, and it's inside of this cone over here. Yeah, in this case, I don't think the drawing is too significant, or in terms of the, in terms of the labeling and everything though. So let's get into that. So we'll quickly sketch this. I realize it's easier to draw because in the previous question we only needed the first octant, and this one we need the entire circle. So, or entire sphere, sorry. So it's kind of easier to actually start out with a decent looking circle first. There we go. Let me try to draw a better curve. Yeah, that'll work. And then from here, we can draw the back portion. And yeah, okay, nice. So we'll take this and we'll draw our coordinate axis around it. Is that how I do it? Yeah, something like this. It doesn't have to be exact again. And then, or actually, you know what? Here, let's do it this way. Roughly here, here, then here. Okay, that's much easier to draw. So here's our x, here's our y, and here's our z. Now, so again, this is our sphere of radius root 2. Now we have to draw this out. So it looks something, yeah, something along these lines here. So roughly there, and then yeah, we get a curve going over here. There's that, and then we kind of have like a back portion over here. So I'm just going to sketch this in here so it's a little more clear. But yeah, we have something like this over here, and yeah, sorry, we haven't even gone into the actual question or why we need this yet. But okay. So the idea is we want to use Stokes theorem in this case, which effectively allows us to evaluate the surface integral of a curl using, I forget what it was. Oh yes, just using a line integral instead. We forgot that, but yeah. So the line integral would be across this curve C, which I believe, yeah, it goes this way over here. So that right there is our curve C, right over here. But yeah, okay, so I'll quickly write out Stokes theorem first. So we have Stokes theorem. So Stokes theorem, and it states, yeah, exactly this. So again, effectively relates the surface integral of the curl of a vector field with a line integral. So line integral over C of, yeah, just f dot dr. So standard line integral, and in this case, this is where, yeah, where C, or curve C, is equal to, the notation is, I think, partial, yeah, partial S, but this basically just means the boundary curve. So boundary curve right over there. So yeah, our surface in this case is actually the cone, but the boundary surface or the boundary curve is actually just kind of C over here like that, basically the cone effectively. So yes, let's go to that. So first we need to find the intersection between the cone and our sphere, which isn't too bad to do considering we have two pretty simple equations. And yeah, so here I think we start with the z. Yeah, so we have z is equal to so x squared plus y squared under square root, which then tells us that z squared is equal to just x squared plus y squared. With this in mind, then, we can now make use of the sphere. So we have x squared plus y squared plus z squared is equal to 2. We know that x squared plus y squared is equal to z squared, meaning 2z squared is equal to 2, which then also tells us that z is equal to plus or minus root 2. It's just equal to, z squared is equal to 1, so it's plus or minus 1. Apologies. Okay, in this case, we choose the positive z, again, because our cone is pointing upwards, or it's growing upwards. So here we say choose positive z, or choose z positive. Okay, And then from here, I'll quickly again also remind you of how we want to compute the line integral. So the integral over our curve C of dot dr. It's just the standard, yeah. So standard from A to B of our function, so f evaluated at r of t dotted with r prime of t dt. Or again, r of t is just the parameterization of the curve, and then r prime is just the derivative, and a to b are the limits of integration, which come from the kind of boundary points of the parameterization. So let's parameterize our curve C. So parameterize, did I say curve? Yeah, curve C. So we already have z is equal to 1. Z is equal to 1, meaning what we then have up here, what we then have up here is simply a circle of radius 1. So circle of radius 1. Okay, circle of radius 1, and then from this we can easily parameterize this using sine and cosine. So we have x is equal to cosine of t, and y is equal to sine of t. Let's check to make sure. Yep, and then z is equal to 1. So this right here would be our parameterization, and this is how we're just going to write our r of t. So this right over here gives us that r of t is equal to cos t sine t, cos t sine t, and then 1. And then, yeah, so t is here between 0 and 2 pi. And then we can also compute r prime of t here as well. So r prime of t, again, just taking the derivative component-wise. So we get negative sine t, cos t, and 0. Okay. With this in mind, we can then compute this part right over here. So we would do next, yeah, okay. So we then have f of r of t dotted with r prime of t. It's equal to the following. So our function f is this right over here. We're basically just going to plug in cos t, sine t, and 1 for wherever we see x, y, and z respectively, I believe. Yeah, so this first part we have xz. So cos t times 1, which is just cosine of t. Next we have 1/3 x cubed, so 1/3 cos cubed t. And then finally we have z squared y, or just 1 times sine t, so just sine t. And this is just being dotted with r prime of t, which we have right over here, so negative sine t, cos t, and 0. Yeah, and then we just compute this now. So multiplying component-wise, we get negative sine t cos t plus 1/3 cos to the 4t. And then sine t times 0 is just 0, so we don't need to worry about that part. Okay, so now we can finally compute. So therefore, we can conclude that the curl here, or sorry, the surface integral of the curl on n ds, I believe, yeah, is equal to, again, the line integral c f dr. And now we can put everything together. So this is going from 0 to 2 pi. This portion inside over here, we just computed over here. So we have negative sine t cos t. I'll write that, negative sine t cos t plus 1/3 cos to the 4 t dt. Yeah, and again, I'll write them in brackets. And then from here, we're going to do that same strategy where we simply just split up the integral into sums. So we have the integral from 0 to 2 pi of negative sine t cos t dt. I guess we'll move the 1/3 out. So integral 0 to 2 pi of cos to the 4 t dt. Let me just check my computations here. Okay, so this first portion here is not too bad to calculate. This right here is the exact derivative of cos squared t, and of course, or sorry, 1/2 cos squared t. So 1/2 cos squared t. Evaluate it from 0 to 2 pi, and again we can check, take the derivative, we get times 2 cos t times negative sine t. 2 and 2 cancel out, we have negative sine t cos t. This right over here, I'm going to compute on the side. It gets slightly messy, I think. It indeed does. So we'll use the quick double angle identity that we saw previously. So cos squared t, we again know that, or goes from cos 2t, but we know that this is equal to 1 plus cos 2t over 2. Okay, and then if we square both sides, we get cos to the 4t is equal to 1. So this is just a plus b squared. So 1 plus 2 cos 2t, and then plus cos squared of 2t, all divided by 4. And this right here, we can then use this exact same identity once more, except it's just, we're just substituting this in instead with 2t instead of just t. So again, recognize the similarity here. I believe, so cos squared 2t. Again, you can kind of just imagine replacing t with 2t over here, and you get exactly this. So it's 1 plus cos of 4t divided by 2, meaning we can then replace this right over here. How did I write it? Yeah, so cos 4t is equal to 1 plus 2 cos 2t plus this right over here, so plus cos 4t over 2. And this is all being divided by 4. And then a last quick simplification you can do here is multiplying the top and bottom by 2. So this then gives you 2 plus 4 cos 2t plus 1 plus cos 4t. So the 1 I'll just combine over here. So cos 4t. And again, remember we also have to multiply the bottom, and we get exactly this. So now we can effectively replace this with this, and we can also drag out the 1 over 24. And that comes from just doing 1 over 3 times 1 over 8. This right here, we'll just integrate directly just to save some space, cut down on some writing. So this is being multiplied, so 3 becomes 3t. 4 cos 2t, again, derivative of what is equal to cos 2t, 1/2 sine 2t. So 2 sine 2t. Again, take the derivative of this, you get 2 times cos 2t times 2, so you get 4 cos 2t. And then cos 4t, in this case is just 1 over 4 sine 4t. And this is again being evaluated at 0 and 2 pi. Same idea, you can check this as well. So you get 1 over 4 cos 4t times 4, cancels out, you get exactly cos to the power 4t here again. Okay, next we can now evaluate, I believe, So this right here just goes to 0 because cos of 0 and cos 2t are both equal to 1, and then you're subtracting them, so this goes to 0. This, on the other hand, we can actually compute slightly separately, I guess. So you get 0 plus 1 over 24 times, and then here, these all have t's in them. Sine of 0 is also still 0. This doesn't really matter. Sine of 2 pi, or any kind of even multiple, or any multiple at all of 2 pi is also equal to 0. So here you're just left with 3t, or 3 times 2 pi, so 6 pi, which ends up being what, pi over 4? Yeah, pi over 4. And yeah, that's how we finish this question. Question 12. Let S be the boundary of the solid that is enclosed by the surfaces z is equal to 1 minus y squared, y is equal to root z, sorry, y is equal to root x, z is equal to 0, and x is equal to 0. In this question, we want to use divergence theorem to compute the surface integral, where this is what our function is equal to. So the idea is here, similarly, it's going to be somehow difficult to compute this with the fact that our vector field is equal to that, which is where divergence theorem will come in. So first we'll sketch the solid and then we'll proceed from there. So, yeah, something like this should be good. How much did I angle it down? Okay. Yeah, good enough. Okay. So this is our x, this is our y, this is our z. Okay. So first, I guess we can start by sketching the bottom portion over here. It's going to look something like this. This right here is just going to be our y is equal to root x. And I think we were bounded by 1 somehow, some way. Oh yeah, I guess so, yeah. Because we're bounded by z is equal to 0, we can see what happens when z is equal to 0 here. So in this case, y is equal to plus or minus 1, but because we're dealing with this portion over here, we just have y is equal to 1 over here. And just to clarify, this right over here, if we look at, if this was like, let's say, for example, y is equal to 1 minus x squared, we know this is just a parabola that goes downwards like this. But because we're dealing with 3 dimensions, it's actually a cylinder. And it's more of like a parabolic cylinder. It kind of goes like this, but like infinitely into space. And yeah, it kind of goes along the x-axis. So imagine like something like this, but like again, yeah, it goes on forever pretty much. And the intersection between that and z is equal to 0 is this line right over here. So I'm just going to draw that. Something like this. And then I labeled it y is equal to 1. So yeah, this right here is just a region that's, oops. So yeah, that's the region in the xy plane pretty much. And okay, so next, yeah, when z is equal to 0, that's again what happens. Now we can take a look at what happens when x is equal to 0, meaning we're looking at the yz plane. So when x is equal to 0, we pretty much just have exactly this. So we can imagine, again, a parabola, basically. Okay, and then within that parabola, when y is equal to 0, x is equal to 1. I believe, yeah, so let's say 1 is somewhere. Actually, no, I labeled this as 1. So let's draw a diagonal line. Okay, so roughly right over there is where 1 will be. I'm going to draw like a parabolic arc down here. Very good. And then the last portion, yeah, this last portion is more of like a connecting line that I'm going to draw down. Yeah, just like that. Okay. So the justification behind kind of where this line really comes from is you can imagine having that kind of cylinder being cut by like root x. And remember, root x, y is equal to root x in 3-dimensional space is effectively the same thing as your 2D root x, but kind of infinitely up and down in the z direction because it simply doesn't appear, right? So that's kind of, it's slicing through that portion of the cylinder in like this kind of first octant area pretty much. Okay, so now I'm going to quickly state divergence theorem over here. So divergence theorem. So the divergence theorem simply relates the surface integral, where is it? Yeah, this right over here, to a triple integral over a solid that basically the surface kind of encompasses or surrounds. So let me show you. So in this case, we have the following. S, and then, yeah, so f dot n ds. This is again just equal to triple integral over solid E of the divergence of f and then dv. So yeah, in this case, the E is this solid right over here that's kind of bounded by that surface S. Excuse me. So yeah. Now, obviously, looking here, we need to compute the divergence of F, which is a lot easier than the curl. So the divergence of F, again, you can always remember an easy way to kind of, I guess it is remember, but remembering that the divergence is the gradient dotted with our vector function F here. The curl is simply the cross product instead. So in this case, what that then gives us is, this is equal to partial, I guess we should label this too. So P, Q, and R. So partial P, partial X, plus partial Q, partial Y, plus partial R, partial Z. Yes, okay. And now we can actually compute each of these. Yeah, okay. So partial P, partial X, we'll compute over here. Again, we're only looking at parts of P here that contain X. There's no X over here, so we're simply looking here. So we have a 2. Partial Q, partial Y, same idea. We're just looking for Y here. Nothing over here, so it's just a -1, so plus -1. And then partial R, partial Z. Z doesn't appear at all, so that's just a 0 now. And then 2 plus -1 or 2 minus 1 is just equal to 1. Okay, and then we'll also here quickly on the side now sketch the XY plane projection, just so that we can move on to the next step, which is to basically find a quantification for this solid E. So projection. This one is pretty straightforward. We literally just have y is equal to root x, so it looks something like this. This is again not really going to be to scale, it's just a rough sketch. Yeah, let's say that, and then we can draw this line back here. So let's say this here is 1. This is again y is equal to root x. Do I convert? Yeah. So in this case, we'll also just rewrite this as x is equal to y squared. It'll be useful for later on when we decide to, or again, yeah, quantify this solid. I sketch, yeah, dude, can definitely sketch it in. So, ooh, that's bad. Yeah, good enough. Yeah, okay. So we'll quickly, I guess, yeah, it's a bit hard to see, but yeah, this kind of surface here is effectively z is equal to 0. And then the cylindrical part is kind of this part over here, so z is equal to 1 minus y squared. This part back over here is kind of, you can think of it as being created from x is equal to 0. The labeling doesn't matter that much as long as you kind of have that intuitive understanding of where that all comes from. Okay, so next we'll describe the solid E. And I'll just use set notation. Or actually, yeah, just E set. So we have our points x, y, z. Yeah, right. Yeah, such that, okay. So in this case, first we'll look at our xy projection, I think. Yeah, we decided to go with y between, or in this case, it really doesn't matter which order you do it in. I just happen to go with the exact same, I keep saying quantification. I'm not even sure if that makes sense, but I just go with the quantification that the instructors use, which is seeing this as a type 2 region here. So you're squishing your function between two constant y values, and then you're writing x in terms of y. So let's go with that. So y goes between 0 and 1. 0 and 1, I believe. Yes. X, on the other hand, we can take a look here. So start from the bottom, go to the top, ends up here. This is x is equal to 0. This is x is equal to y squared. So x is then between 0 and y squared. And finally for z, we know that z equal to 0 is just the xy plane, which is precisely where the bottom is. So we start at 0. And then the function on top is exactly over here. Conveniently, we just have it as 1 minus y squared. Okay. Okay, and then from here, now all we have to do is just compute this portion over here. So, therefore, the surface integral of so f dot n ds is equal to, and then we can set up the triple integral now, or we'll set it up in the next step. So triple integral over our solid E, which is 1 dv. And also you should recall that effectively this is just finding the volume of the solid pretty much. Okay, so now we can actually set up the triple integral. I believe, yeah, so the inside will be our dz part. I'll set it up like this so it's fully clear. So this is D, or region D, which is again our xy plane projection. And then yeah, I'm starting like this so it's super clear. This is just our z portion now, and our z goes between 0 and 1 minus y squared. And then our function is just 1 and then dz, dA. And yeah, and in the next step I just expanded anyways, I think. So yeah, so we have the integral here now. And yeah, so in this case, y goes between 0 and 1. X goes between 0 and y squared. And then z goes between 0 and 1 minus y squared. And you have 1 dz. And then this is again our x, so dx. And then dy, I think, yeah, dx dy. Very good. And then now we can simply just evaluate this. So z doesn't even appear here yet, so we integrate it. It just gives us that z. So we have 0 to 1, 0 to y squared, of just yeah, 1 minus y squared, then dx dy. Here, similar idea, we can just append on this y squared now, so we have the integral between 0 and 1 of, yeah, this becomes, again, just x evaluated at 0, y squared. You get this part, so this is just y squared, so we have y squared minus y to the power 4. dy, I believe. Yeah, and then from here we can directly integrate this. So this becomes 1/3 y cubed minus 1/5 y to the 5. And this is all evaluated between 0 and 1. 0 obviously won't contribute anything because we have y everywhere here, so we simply just get 1/3 times 1 cubed minus 1/5 times 1 to the 5, which is also just 1/5 still. And then yeah, this we can find the common denominator, so it's 5/15, so 3/15, so 2/15. And that right there is your final answer. So that's it. Again, watch over as many times as you need, go back, slow things down. Some parts I didn't provide a full justification for, or it's kind of hand-wavy, but again, the intent of these videos is mostly just to help you through the solution. If you're taking MAT235, I think it's almost safe to assume that you don't care that much about the actual theory and like the rigor of everything, which is the case for me as well. But yeah, thank you for watching.